In this video, we're going to talk about the measures of the spread of data. So what we're going to be looking at is a way of kind of understanding how spread out the data is. We have briefly touched on it when we looked at box plots. We talked about how the minimum and maximum, when you look at their difference, that gives us a range of the data. So the difference between the highest value and the lowest value. That's nice information. And of course, the bigger the range, the more spread out the minimum value and the maximum value are. But it doesn't give us as much information as we like. So we're going to introduce this concept called the standard deviation. Now, the standard deviation gives us a numerical measure to kind of overall look at the variation in the data. We use it to kind of figure out if data is close to the mean or far from the mean. The standard deviation is always a positive number, or it could be zero. When it's small, that means the data is close to the mean or concentrated around the mean. And when it's larger, we expect it to be further away from the mean. The data is more spread out. So let's kind of look at an example where we talk about standard deviation. So suppose we have two supermarkets, both who have an average wait time of 5 minutes. Supermarket A has a standard deviation of 2 minutes, whereas supermarket B has a standard deviation of 4 minutes. So we see that for supermarket A, they tend to have more consistent wait times. They tend to be grouped around 5 minutes, where for supermarket B, a lot less consistent wait times. You might wait quite a bit longer at supermarket B or very short at supermarket B because the standard deviation is so large. So we're told that two people, Rosa and Ben, are shopping at supermarket A. So we're going to, for the moment, ignore supermarket B, though I am going to talk about it afterward. Rosa waits for 7 minutes. Ben waits for 1 minute. Okay, so Rosa's wait time of 7 minutes. So we're told that the mean is 5 minutes. Oops, that is not how you spell minutes. There we go. 5 minutes. And since she waited 7 minutes, that means that she waited 2 minutes above the mean for a total of 7 minutes. Well, 2 happens to be what they said the standard deviation was, right? Standard deviation is 2 minutes at supermarket A. So she is 1 standard deviation. I'm going to use SD to represent that standard deviation above the mean. All right, so let's look at Ben now. Ben waits for 1 minute. So comparing that to the mean, that would be 4 minutes smaller than the mean, right? Well, 4 minutes is 2 standard deviations. So Ben is 2 standard deviations below the mean. All right. So what do we conclude? So here's what that tells me. When data is within 1 standard deviation of the mean, that's expected. To be within 1 standard deviation of the mean, we're very comfortable with that. So Rosa's wait time is very expected in this problem. This is kind of a reasonable thing to see happen. However, Ben's wait time of 1 minute is less expected. 2 standard deviations away from the mean becomes less expected and less likely to happen. So the further a data value is from the mean, the less likely that data value is going to occur. So we kind of have this idea that Ben got lucky, really lucky, right? The odds were kind of against him having a 1 minute wait time. But for Rosa waiting 7 minutes, that's kind of expected. We're not thinking that's a very shocking number. If I had changed all of this information to be at supermarket B, in that case, then Rosa is like half a standard deviation away. Okay, so she's not even 1 standard deviation away from the mean. And then Ben would be 1 standard deviation away from the mean. So both of their wait times would be expected at supermarket B. All right. In fact, Rosa could kind of count herself lucky because only waiting 7 minutes at supermarket B, waiting 9 minutes wouldn't be unheard of. All right. Okay, so what I kind of said there, I put here in a note. When a data value is two standard deviations from the mean, they kind of borderline that on being what they call far from average. Okay, it's less likely to happen. So let's talk about how we even find the standard deviation. Just like a mean, standard deviation has two representations. When we're talking about a sample, we're going to use S to represent the standard deviation. And when we're talking about a population, we're going to use lowercase sigma, which is like a circle with a tail on top. That represents the population standard deviation. Okay, so we're going to kind of derive this formula in steps. What we're going to do is we're interested in how far every data value is from the mean. So what I mean by that is I'm looking at the difference between each data value. So we use x sub I to represent any data value. So x sub I minus the mean. So if I'm talking about population, it would be mu. Or I could be talking about a sample. If I'm talking about sample, I would be doing x bar. So I'd be subtracting every data value from, and then subtracting the mean from that value. Okay, now what's going to happen is some of the values are going to be bigger than the mean and some of the values are going to be smaller than the mean. So we're going to get a bunch of positive numbers and negative numbers. What I want to do is I want to find an average. I want to find the average distance each data value is from the mean. Therefore, I want to add these all together, but if I add a bunch of positives and negatives together, they're going to all cancel out. So to solve that problem, we're going to square each data value. Now, there is another option. The other option is to possibly do an absolute value. An absolute value makes all the data positive. But I'm going to ask you to trust that doing an absolute value actually complicates things in the long run. It is easier to just square all the data because squaring a negative value makes it a positive. And then later on, I'm going to undo the square by taking a square root. So I'm going to compensate by taking the square root later on. But before I do that, I'm going to go ahead and add all of the data together. So the symbol we use is capital sigma when we're adding all the data together. But we're adding these squares, these big positive values, all together. All right. And then I'm going to average it out. So I'm going to divide by how many data values there are. When we're talking about population, we use capital N to represent the population size. When we're talking about sample, we use lowercase n to talk about it. Now, we actually are going to do one slight difference for the sample. I'm not just going to use lowercase n when I find this average. I'm going to actually use n minus 1. We're not going to talk about why that is, but that is the case. They call this, by the way, the variance, what we just found right here. This is called the variance. And they use the symbols lowercase sigma squared and s squared to represent the variance. This is not the standard deviation, though. The standard deviation comes when I actually take the square root of this. So the square root is the standard deviation. So when I actually take the square root of this, I get the sum of x sub I minus mu squared all over capital N for population. For sample, I get the sum of x sub I minus x bar squared divided by n minus 1. And that square root is the standard deviation, which I also went ahead and put in a nice neat box below. All right, so let's find the standard deviation in an example. And I just want to kind of say, so what we're looking at is the standard deviation is kind of an average value of how far data is from the mean. Okay, so here we go. So we have this data set, and it represents 9 random casts so that they're taking a sample here. Okay, it's important. We have to distinguish when we're doing standard deviation, whether we're talking about a population or a sample, because the formulas are different. Okay. So in this case, they're taking a sample because there's 9 random casts. That implies a random sample. And I need to find the standard deviation. So I'm going to organize this in a little table. I am going to need to find the mean though. All right. So if I add these all together, I got 33,030. And then dividing that by 9 is 3,670. Okay. So I'm going to, here, let me zoom out a little. I'm going to take all of these data values and I'm going to put them here in the table for X. So this is 3960. So we often use X when we're talking about a piece of data. Sometimes they use X sub I, but in statistics, that's what we're using to represent our data values. All right, and that's 3780. All right, so there we go. There's all the data. So what I'm going to do now, and I encourage you, as I'm doing these calculations pretty quickly, pause, make sure you do the calculations and verify the numbers are going to match. I'm going to take each data value and I'm going to subtract 3,670. So for the first data value, when I do 3960 subtracting 3,670, that's going to give me 290. And then I'm going to get 420 when I do 4,090 subtracting the mean. Here I'm going to get negative 470. So my first negative value, because it's smaller than the mean. This one's negative 570. Negative 730. 160, back to the positives, 420. This one's the same as the, that last one I just wrote was the same as the second value there. 370 and 110. Okay, so I'm going to square each of these. And remember, when you square these, if you put it in the calculator, you do need to put parentheses. I kind of indicated that by putting parentheses around this top thing. The reason is the calculator, if you don't put parentheses, but you put a negative, the calculator is going to assume the negative carries into the answer. But we do not want that. The whole point of squaring this is to get rid of the negative values. So all of the negatives are going to go away when we square this. So this first one is going to be 84,100. Again, pause the video, calculate it really quick, verify we match. 176,000. There we go. 400. I knew I could do it eventually. 220,900. 324,900. 532,900. 25,600. 176,400. 100 and that's a 7. Sorry, let me fix it. 7. Okay. 136,900 and 12,100. So for a grand total of 1,690,200. So to do the standard deviation for the sample, I'm going to divide this by 1 less than the data values. And I had 9 data values. So I'm going to divide it by 8. So when I divide this by 8, I get 211,275. And when I take the square root of that, I'm going to actually just put it in like that. That's going to give me 459.6. So that is my standard deviation.